Welcome, loyal students. In this video, we will look at the more advanced topics of liquids, including the Clausius-Clapeyron Equation. This one you may need to pay a little bit more attention to because it is a little bit more challenging. So we will go ahead and get started. Okay, so one of the first concepts we need to discuss is the idea of vapor pressure. The idea is that as a liquid warms up, the molecules will gain more kinetic energy, and we're going to see a kinetic energy profile similar to one we saw last semester when we looked at gases. The idea is that some of the liquid atoms will have higher energy, some of them will have lower energy, lower speeds, and the amount of gases with higher energy will increase as we increase in temperature. That you can see right here that at 300 Kelvin, the majority of gas molecules are at this speed. At 320 Kelvin, it's kind of shifting more over, so we have more more liquid molecules moving at a higher rate of speed. But at any given temperature, there is some portion of the liquid molecules that have enough kinetic energy to achieve essentially escape velocity, and thus they will become a gas, in this case a vapor, and thus they will generate a pressure based on this escape velocity. Because some of them will generate a gas, so we're going to generate a vapor pressure. We talked about this last semester as a gas and gas chapters, that liquid water has a vapor pressure that is directly dependent on the temperature and not dependent upon anything else. And that's because the temperature of that water will tell us how many water molecules will be able to achieve escape velocity. As you see here, that bromine, as we heat it up, we have more molecules can escape from bromine. You can have more molecules escape from water. It all depends on what it's mixed in with. Different liquids going to have different intermolecular forces, so it's going to have different regions where it needs to escape. But simply put, this vapor, it works both ways. For every liquid molecule that can escape into the gas phase, gas molecules, if they collide with the liquid, will become trapped. But we have a constant push-pull of molecules escaping and molecules being trapped at the same time. Gases dissolve into liquids because the gas molecules like oxygen and nitrogen hit the liquid and get stuck for a time, but they will also come out again. In a closed container, this process of leaving and returning will reach a steady state, which we call an equilibrium. We will talk more about equilibrium in the next couple chapters, but for now, just know that it's a steady state where if you have a closed container, there's going to be a maximum amount of gas molecules present from the vapor. That once you get so many, there's going to be a greater amount of liquid molecules being trapped as opposed to the solid molecules going, as opposed to the liquid molecules escaping. So in an open container, though, the liquid will eventually all escape into the gas phase. So if you leave a glass of water on a counter for a couple months, it will eventually go dry because enough of the liquid will have slowly leaked out. Because if the gas is allowed to expand and keep going, the likelihood of that liquid hitting the gas again, the gas hitting the liquid again, is decreases, and so it just slowly evaporates. Now, some liquids, because they have very weak intermolecular forces, are said will readily evaporate. And so these guys are said to be volatile. So these guys, volatile gases, typically if you open up a container and you can smell something, you probably have a volatile gas. You have something that is readily willing to evaporate into the gas phase, go up your nose, and hit your smell sensor molecules, smell sensors, and thus you can detect it readily. That is known as a volatile gas. Now, there are some things that are very hard to vaporize. Those guys would be very non-volatile. But largely speaking, having a volatility and a high vapor pressure are signs of having weak intermolecular forces. So that these very easy to escape and very readily escaping means there's not a lot of forces that are holding the liquids in. Well, a gentleman by the name of Clausius, Rudolf Clausius, we talked about him when we talked about the kinetic molecular theory of gases. Well, he also worked with a gentleman by the name of Clapeyron to develop an equation that you may learn to hate. But it directly relates the vapor pressure of a gas to a given temperature. That this is indirectly proportional to the vapor pressure by a value of the enthalpy of vaporization. That enthalpy of vaporization is going to control, so how much energy it takes to vaporize is essentially the escape velocity. And that's going to be directly related to the temperature in Kelvin, and that's going to generate our vapor pressure. So the whole equation looks like natural log, so ln. This is completely different from our standard log. So please know the ln function on your calculator. Find that. Find it on the calculator. Some calculators have it on the same button, some of them have it on different buttons. But the ln function of a pressure of vaporization is equal to the negative enthalpy of vaporization divided by the gas constant R. This gas constant will be in joules per mole Kelvin, and it will be given, but it's something we'll have to use. And we have to make sure we use the same one, the right one. And that's divided by the temperature in Kelvin. And then you add in the natural log of our beta value. The beta is a constant for a given liquid. Now, this right here is a graphical equation we can do. However, if we change the temperature and remeasure the pressure, our beta will drop out. And drop out, the beta will fall away. And so we get a new equation that simply measures the graph of the ln P vaporization 1 over the P vaporization 2 is equal to enthalpy of vaporization over R. And here's, you notice we lost the negative because the negative went into here. 1 of T2 minus 1 over T1. Normally it'd be 1 over T1 minus 1 over T2, but by pulling the negative into here, you can sometimes reduce complexity, but it would be one where I'll be giving, there is 1, 2, 3, 4, 5 pluggable things that are capable of changing. You will be given 4 out of those 5 typically. And so as long as you can link the temperatures with pressures, you can solve this. It is a little bit more challenging. And I hate to throw you this challenging problem right off the bat, but this is an equation that we will see in other forms. Even though it won't be P vaporization, it is something we will see again later. So I want you to be familiar with it now. So, and we'll work on these 2 problems. Now, one thing to note, as long as your pressures remain the same, you can leave the pressures in whatever units you're given. You do not have to turn the units into something else. So, if water has a vapor pressure of 23.8 torr. 23.8 torr at 25 degrees C. What would we expect the vapor pressure at 0 degrees C? If the enthalpy of vaporization is 43.9 kilojoules per mole. Now there's one thing I have not given you, and we will get to that in a minute. But step one is to set this up. I'm going to try to set this up using this. So our equation is ln, the P1 over P2 delta H over R 1 over T2 minus 1 over T1. We're going to solve this in parts. Now you might run into a problem if you leave these in Celsius. One of which is you cannot divide by 0. We need to convert these into Kelvin. That is a common occurrence in these coming chapters, as we will almost always work in Kelvin. So if you have not converted things into Kelvin, do so. Now, it does not matter which one you call T1 and which one you call T2, as long as you link them together. The known, what I want, is linked with that. I'm going to call that V1. And you'll see why in a minute. But you could absolutely solve it either way. So if this is V1, this is T1. If this is V2, if that's P2, that's T2. So I'm going to start. I'll solve this one step at a time. 1 over 298 minus 1 over 273. Do not round. Try your best not to round. Keep the number at least to 3 or 4 sig figs. Do not round unnecessarily, or you will run into some problems. Because we will be dealing with a very small number. So this is negative 0.000307. I'm going to say 30. I think that's safe. That's 5 sig figs. I probably could have kept 4 sig figs, but 5 sig figs, that's more than safe. Now, that's a negative number. Now our enthalpy is 43.9 kilojoules per mole. Our gas constant, R. If you're like, where did he pull this number? He knows this number. Of course he does. But where would I get it? It would be on the useful information sheet. It would be a given on the test. It would be something that would have to be shown. It would be on the hint in the problem. So 8.314 joules per mole Kelvin. So what does that mean? In order for this is in 1 over kelvins. 1 over kelvins. In order for this to work, we need this into joules or this into kilojoules. So I'm going to turn this joules per mole Kelvin, I'm going to multiply this number by 1,000. That's going to turn that into joules. Joules will cancel joules. Moles will cancel moles. 1 over kelvins are going to cancel 1 over kelvins. 1 over kelvins. So I'm going to multiply this by 43.9 times 1,000. And I'm going to divide that by 8.314. So my number, I'm going to keep at least 5 sig figs. 1.622. Let's see. 6. Now, you'll see why. If I said 0.0003 4307. Let's try this. 43.9 times 1,000 divided by 8.314. That gets negative 1.6210. And what if I said 0.00031? 31. I rounded again. If I rounded, you will see why rounding is a bad thing. Rounding unnecessarily. 8.314. So this is maybe 3. Well, let's say I'll round it to there. Okay, this is most accurate. So, right here, all this I've solved for this right half of the equation. My left half of the equation reads like this. Because I have said this is P2, I have ln P1 over 23.8 torr. Right now, this number is unitless. It's unitless. So, the units of my answer are going to be directly dependent on this. So, we need to get rid of this natural log. The way we get rid of this natural log is a function called exponential, the exp. Exponential. I want you to look on my calculator. It is the e raised to the power. E raised to the power on my calculator. It is exponential is a certain type of constant, much like pi. So if I said e to the first, the magic number is a number that doesn't really repeat. It's 2.718281828, and it keeps going forever. But the exponential of a natural log of a number, they cancel each other out. If I take the ln of e to the 2, they cancel each other out. So in order to solve this, I'm going to take an e to this side and an e to this side. And this is going to cancel out. So I've now solved this as P1 over 23.8 equals what this number is. So let's look at my numbers. So if I take e, let's do the most accurate one, the one that should be right. 1.6226. I get 0.19738. If I did the slightly less accurate one, negative 1.621, I get 0.19770. And if I did the even slightly less accurate one, 1.637, 0.19456. Okay. Either way, none of these are the answer yet. I know it takes a while. It takes a while. We want to know what this is. We have P1 over P2. So to get P1, we have to multiply both sides by P2. 23.8 torr cancels that out. But I also have to multiply this side by 23.8 torr. So our pressure at 0 degrees, so 0.19738 times 23.8 torr, the correct answer is 4.698. That's the correct answer, or the best answer. But let's see how this affects my other possibilities. See how much it throws my answers off. So the second one which is still somewhat accurate, 4.705 torr. Let's see, 0.19456 times 23.8. We get 4. We get 4. Let's see. 631. Okay, so most of these are, let's see, 4.698 minus 4.631. Okay. Now, thankfully, while this is the most accurate number, these guys are not far enough off to be wrong. These guys are not far enough off to be wrong. However, sometimes if you round, especially if you round only to this one spot, these numbers can creep up and you can get a large enough difference that it will matter. So try to keep as many digits as you can when you're doing the really small numbers like this. Try not to round over zealously so that we don't goof up our numbers too badly. So, with that in mind, that is that problem. That was a doozy of the first major problem. Now, we're going to do this again. Do it again. Now, we're saying in this particular problem, if a liquid with a heat of vaporization of 50 kilojoules per mole has a vapor pressure at 35 torr at 50 degrees C, what would the temperature be at 70 torr? So we have a delta AH of 50 kilojoules per mole. We have a temperature, a pressure of 35 at 50 degrees. Well, we have the pressure of 70 torr at what? Now, here is something I'm going to show you how to do. Something that is very useful. If you learn how to use Excel or Google Sheets, this will help you in the long run. So real quick, Google Sheet knowledge. We can write in various equations into Excel and Google Sheets by typing equals. I can type any number I want. I can say 5 plus 10, and I can type, and it will sum them up. I can heat 51 times 89. So the asterisk is the multiplication, and it can do that sign. I can do 78 divided by 98, and it will give me a fraction. I use a backslash. I can do division. I can do exponentials. I can do exponents. I can say, what's 4 raised to the 8th power? I use a caret. So one thing to note, I can do whatever I want as if I had a calculator in here. And if I scroll back over the particular box, it will tell me what the formula is up here. Let's see if I can. It will tell me what the formula is up in the function box. Okay. It will tell me what the formula is in the function box, and it will also give me the answer. Now, this will be very useful if you don't want to have to save things in a calculator and you don't want to have to worry about rounding. Now, with that in mind, I can write whatever equation I want. I'm going to write right now, just a quick reminder, the equation we want is ln P1 over P2 equals dH over R 1 over T2 minus 1 over T1. Just showing you here so we can go, oh yeah, that's what we're trying to graph. So let's say we have P1. That was 35 torr. Put P2, that is 70 torr. T1 was 50 C. And 50 C. And T2 is, we don't know. So with that in mind, one thing we'll have to do, we'll have to turn to temperature in Kelvin. So we can say equals 50. We can either type in the 50 or we can actually refer to the box. Since I have typed this into box G7, I can scroll over and refer to box G7, and I'm going to add 273 onto that. So that's my T1 in Kelvin. Now our DH is, of course, actually I'm going to move that over. DH is, as I said, 50 kilojoules. 50 kilojoules. We're going to want to turn that into joules. So we're going to say equals this box times 1,000. That's going to give us our DH in joules. And our R constant is 8.314 joules. Now, with that in mind, let's graph. I can say, to do a natural log, I just have to say equals ln, and you notice it shows right there, returns a natural logarithm of a number. I put parentheses and I say whatever number I want in there. So what's P1 over P2? So 35 over 70. I can either do the box or the number itself. P1 over P2 gives me this number. Okay, it gives me the full number. I can either, if I want to give it to more decimal places, I can zoom out and I can figure it all out if I want. Now, the next step is to get the R and the delta H to the other side. So to do that, I'm going to take my answer and multiply it by my R and divide it by my delta H. At this point, so this was the ln P1 over P2. Now this is going to be the ln P1 over P2 times R over DH. At this point, I need to get 1 over T2 by itself. So to get that by itself, I have to add 1 over T1 to my answer. So I'm going to equals whatever this is, and I'm going to add 1 divided by my T1, whatever that number is. Notice I get a positive number, which is good. If you do not get a positive number, you have done something horribly, horribly wrong. You can never have a negative temperature in Kelvin. Impossible. So with that in mind, the last thing is to get my temperature in Kelvin over 1. So to do this, I'm going to say if 1 over T2 is this, 1 over this is the inverse. I can do it like that, 1 divided by that, or I could do it as I raise this to the power of -1. Gives me the same number. Finally, I could turn this back into Celsius by subtracting 273.15. And I get, at what temperature will my vapor pressure have doubled? At this enthalpy, it will have doubled after at 62.5. Now the beauty of this is with these two data points, I could actually graph this. And the slope of the line would be, 50 over r, delta H over r. And the y-intercept, though we don't have it right now, would be the beta, the ln of beta. But so we could look at this and keep going, keep figuring out our relative temperatures. Now that's a little bit advanced, but if we learn how to use our Excel, it is a great tool. It is a calculator to the extreme. It allows us to essentially do whatever we need to do on a calculator, but store more functions and do it more efficiently. So I will slowly be introducing this back into things. But you may still have to set this up on paper to help see what we need to do. But if you've identified what each thing is and what each step needs to be, we can do this on Excel just as easily as you can do it on a graphing calculator. In fact, you can do it more easily if you learn how to do it. But okay, that is that practice. Now the last thing I have is a phase diagram. A phase diagram is a diagram that looks at the effect of vapor pressure versus temperature. So we have that heating curve where we look at, what is our state of matter based on the heat flow and the temperature? Well, we'll learn that pressure, if you apply an external pressure, you can cause more of the gas to turn into a liquid, or more of the liquid to turn into a solid by applying different pressures. So this is a combination of the two, where we're looking at energy and temperature as a form of what state of matter would be present and where do the current lines go. So a heating curve looks at the energy needed for a phase to occur at a constant pressure. So, but pressure affects these guys. So varying a heating curve with various pressures will generate essentially this phase diagram. That will show you, if you know the conditions, you know what is the most stable phase of each thing. So the diagram is separated by 3 lines, typically. Line 1 is the phase change for fusion. So what it takes to melt or freeze a liquid, melt a solid or freeze a liquid. It doesn't look at the energy associated, just at what temperature can it occur typically. We will look at the energy it takes to boil a liquid, vaporize a liquid, or condense a gas back to a liquid. And we will look at the line of the sublimation condensation point. At what conditions will ice just randomly sublimate or water vapor condense back into ice? Now these 3 lines come together at a point called the triple point. This triple point is a unique set of conditions in which all 3 states exist simultaneously. So one thing to note is that when you're at a phase change, when you're, for example, at 0 degrees Celsius, ice is melting, but water is freezing. You have a little bit of ice and you have a little bit of water. Depending on the heat transfer, you might have more ice or more water, but you have ice and water. When water is at boiling, you have some water vapor and you have some liquid water. A large, depending on how much temperature is going into it, you get different amounts of liquid versus gas. Well, at the triple point, it means we have some solid, we have some liquid, and we have some gas present all at the same time. There's one other point that of note, and I think we'll talk more about this on the next slide, which is the critical point. The critical point. It's where the heat of vaporization point dies, essentially. So, as you notice in the phase diagram, the pressure affects the boiling point of the liquid and it's freezing. Well, the boiling point, we know, or we should know, that the boiling point on a mountaintop is lower. We have a lower pressure. So if you're on the mountaintop and you need to disinfect some water, make sure to kill it of microbes, you have to heat it and boil it for a longer period of time, because you cannot get a high enough heat otherwise to kill the microbes. We cook food faster in a pressure cooker, mainly because pressure cooker puts the liquid at higher pressure and we can achieve a higher temperature. And so it cooks faster because we break that barrier of 100 degrees Celsius. That is the maximum cooking temperature at normal conditions. But because in general, as pressure increases, the gas-liquid transition temperature increases. So gases need more energy to escape because the pressure is pushing them down. But the idea here is that for a critical pressure is there's a limit to this trend. There's a certain amount, a critical amount, at which this perfect relationship breaks down. There's a critical pressure and critical temperature. So once pressure gets so high that gases essentially become indistinguishable from a liquid, that we form a special state of matter called a supercritical fluid. So it's above the critical, supercritical fluid. The idea is that the pressure keeps them contained to some extent, but they have enough, and normally they would condense into a liquid, but they have enough kinetic energy, they have enough temperature that they're not really bound strongly with intermolecular forces. That it acts like a gas, which means it has an indefinite volume. It can expand to fill a whole container, but because of the high degree of pressure, it can interact with things as if they were a liquid and dissolve them, so it can act as a solvent. So we often see this as supercritical CO2 is one way we can decaffeinate coffee. That's in a safe method. Or we can use this as a dry cleaning fluid, supercritical CO2. The idea is that CO2 is very nonpolar. When you depressurize it, it evaporates and it will drag whatever it's dissolving with it. So you use this to remove the largely nonpolar, largely hydrocarbon caffeine in the coffee. And you can use that without using harsh chemicals that could be toxic to the body. Same thing with the dry cleaning fluid. That we can use this if you can achieve the high pressures needed, you can use that to remove stains without using toxic chemicals. But so, in general, we may be required to analyze a chart like this. So, when in doubt, check your units. The units on the chart may be different. So it may be in Celsius in temperature, it may be in Kelvin. Do we have negative temperatures? The units of atmosphere may be in, the units in pressure may be in atmosphere, may be in torr, it may be in, it may go by factors of 10. So check, make sure it's scaled properly. This is a logarithmic scale, essentially, so that we can see the big pressures needed. So a logarithmic scale can sometimes make things a little bit harder to read. So what state would it be at 10 atmospheres and negative 60 degrees C? So negative 60 degrees C is about right there. 10 atmospheres right here. If you're at 10 atmosphere pressure and negative 60 degrees C's, you would see a solid chunk of CO2. Under 1,000 atmospheres and 80 degrees C, scroll over, you're going to have 80 degrees C, it's a supercritical CO2. And what temperature will dry ice sublime at standard pressure? That's already given right here. Standard pressure is 1 atmosphere. So dry ice will evaporate at negative 78.5 degrees C. So if the temperature is above that, it will start to essentially boil straight from the solid to the liquid. But dry ice is a very convenient way to keep things cold because as it boils, it's trying to cool things down to negative 78.5. And as it sublimates, it will produce a gas instead of a liquid, so your things won't get soggy. It's preferable to ice for that reason, that you can store things cold and it slowly boils away. You just create a gas and so you don't potentially ruin things. So the triple point, some of these guys are already labeled, but normally when I give this as a test question, these guys are not labeled, so you would have to approximate. But using your eyes is usually good enough. You should be able to get close. But that is the advanced topics for this chapter. We will finish up by talking about solids for the rest of this chapter.